This video is about differentiating exponential functions, such as a to the power of x, where a is a constant. We can try differentiating it from first principles. dA to the power of x equals a to the power of x plus dx minus a to the power of x. A to the power of x plus dx can be expanded using exponential laws to become a to the power of x times a to the power of dx. Therefore, in total, dA to the x equals a to the x a to the dx minus a to the x. Factoring out a to the x, you get a to the x times a to the dx minus 1. Like always, you factor out a dx and replace the other dx's with h's, which you take a limit of as h approaches 0. Because a to the x doesn't contain a h, you can take them out of the limit. Now we need to calculate the limit as h approaches 0 of a to the h minus 1 all divided by h. We come up with a function which we call ln of a, such that ln of a is the limit as h approaches 0 of a to the h minus 1 all divided by h. For example, ln of 2 is the limit of 2 to the power of h minus 1 all divided by h as h approaches 0. We end up with an answer of about 0.693. Similarly, the ln of 3 is the limit of 3 to the h minus 1 all divided by h as h approaches 0. Here we get an answer of about 1.099. Here is a graph of ln of x on Desmos. As you can see, there is actually a point where ln of x equals 1. We call the value of x at which this happens e, so ln of e equals 1. Looking at the graph, we can tell that e is around 2.781. We can find a mathematical expression for e by solving ln of x equals 1. This means we get the limit of e to the power of h minus 1 divided by h as h tends to 0. We will remove the limit symbol and just remember that h is a really small number, as the limit symbol is actually taking up a lot of space. So we move h to the other side, and we get e to the h minus 1 equals h. We also move 1 to the other side, and we get e to the h equals h plus 1. Now we will let n equals 1 divided by h. H is a really small number, so n is a really large number. We end up getting e to the 1 on n equals 1 plus 1 on n. This means the nth root of e is 1 plus 1 on n. Raising both sides to the power of n, we get e equals 1 plus 1 on n, all to the power of n. Remember, n is a really large number, which means we take a limit as n approaches infinity. Hence, we've got our final answer that e equals the limit of 1 plus 1 on n, all to the power of n, as n approaches infinity. You can think of e as being kind of like pi. It is well defined with a mathematical definition, but the formulas for that constant are just limits and approximations. You can't get an exact value using an arithmetic formula, or express it as the solution of an algebraic equation. Just like pi, e is what we call transcendental. It's interesting, as all we wanted to do at the beginning was just to differentiate a to the power of x. We ended with our solution of d a to the power of x equals a to the power of x ln of a dx. While doing so, we managed to discover an entirely new mathematical constant, which we have never heard of before. However, we don't know much about the ln function, except for the fact that there exists a number e such that ln of e equals 1. The next video is dedicated to analyzing the ln function a bit more and figuring out what it really means. So like this video if you enjoyed it, and subscribe if you don't want to miss the next video. Bye.